So, today we are going to be talking about the mole ratio. We talked about last time the how do we use balanced chemical equations for stoichiometry. So, the difference between stoichiometry and balanced chemical equations, or just any type of dimensional analysis, is that stoichiometry is going to use a balanced chemical equation. So, I'm going to write out one for hydrogen, oxygen, making water. So, it's already been balanced for us. We'll get to that in a sec. But we're going to use this for a calculation today. Often I will, instead of writing out balanced chemical equation, we'll use BCE instead. So I'm going to write it out and then just let everyone know that from this point forward, BCE will be the most likely way I'll indicate a balanced chemical equation, though you should be able to check by just looking at the number of elements on either side of the equation to determine if we are balanced or not. So often in these problems, you are given grams of a reactant. In this case, we'll do a problem with grams of H2O has been provided, and you will be asked to find the amount or grams of water that is produced. Now, you could easily be given grams of oxygen, or you could be in reverse, where you could be given how many grams of water, the product, was produced, and ask how much either H2 or O2 was used in that process. So we should be comfortable with both, but we're going to start off with amount of H2. So what we're going to do is we're going to set up a general roadmap for how we will solve this problem. So we'll start off with grams of H2. And just a little side note, in chemistry, we abbreviate, the official abbreviation of mole is MOL. So we just take off the E. It doesn't seem like it saves a lot of time, but we tend to do that a lot. So most often when I'm writing out units of mole, I will only do MOL, though it's kind of silly that you only just whack off the E. Most abbreviations are a little bit more efficient than that. So we're going to go from grams H2O to moles H2O using the molar mass of H2. And then we're going to use the balanced chemical equation to find the mole ratio between H2 and, in this case, water, because that's what we're trying to find. This is what's new to this problem than the problems that we did last week. We will then go from the mole ratio, so we basically convert from moles of H2 to moles of water, and once we have moles of water, we'll use the molecular weight of water to determine how many grams that represents. So next thing we're going to do is I'm going to give you an amount. So we're going to practice this with actual values. So you'll want to get out a calculator to do this calculation alongside. So I'm going to start off by the value I'm provided. So that is grams. It's a unique value. But before I even put any values in, we're going to just lay it out. Now, the most important thing that I'm going to show here is that we're going to cancel units. So I have grams of H2 on top. That's the unique number. So I'm going to come in with red and cancel out grams of H2, showing you that those have been canceled. So that is important. So if I want to cancel a unit, I go and multiply it by something with those units on the bottom. And then I try to figure out where am I going. So I want to go to moles H2. So I know there's a relationship between grams and moles for H2. And now I have moles of H2. I want to get rid of moles of H2. So I write that unit on the bottom. And I want to do the mole ratio. So I want to go from moles of H2 to moles of H2O. So I'm going to put moles of H2O on top. But first I'm going to cross out. So actually I'm going to show you. I'm putting in the mole ratio, which is a unique part in this step. So in this case, we have for every 2 moles of H2 used, we make 2 moles of water. So now the moles of H2 canceled. We're left with moles of water. So the next step is to go from, so we're going to show that those cancel. We want to go to grams of H2O produced. And so we're going to multiply, oops, didn't want the red ink, better get rid of it. Back to black. Whew, that feels better. All right, so we're going to go moles of H2O on bottom because we want those units to cancel. And we're going to have grams of H2O on top. That's what the units we want to end up with. Okay, so now we have this. We have grams of H2O, so now we can go back through this whole equation, and we can put in the values. So if we look back, I don't think I provided you any values yet, but now it's basically set up where you can put in the initial grams of reactant and the molar masses of H2 and H2O, and you can solve it. So I'm just going to make up a number, 10.5 grams of H2. Then I will put in the molar mass of H2, so one hydrogen is 1.01 grams per mole. And so we'll multiply that by 2 to get 2.02 grams per mole. So we're going to put that in here. For every 1 mole, there's 2.02. Every time we have a mole in these equations, the number should be 1 in front unless it's the mole ratio. Now for water, we have 2 waters, and so that's going to be equal to 2.02 grams per mole, and oxygen is 16.00. Now often we see this as 15.9994, but 16.0 is perfectly fine. So that's 16.0 grams per mole, and then we add those up, we get 18.02 grams per mole. So we're going to go and put that into our expression. Not a lot of room, so we're going to put it right up above with an arrow. That's fine. So get out your calculator, and when you're plugging this in, you can do it a couple ways. The way I'm going to do it is I'm going to take all the numbers on the top. So I'll do parentheses 10.5 times 2 times 18.02 end parentheses divided by parentheses 2.02 times 2 end parentheses. So on a graphing calculator, I like to use that because you can see, you can check your work before you hit enter to make sure that you put in what you thought you put in. And using parentheses is pretty easy to use and to see. And so if we do that, we can see that the value that we should get, now we'll double check to make sure this value makes sense. But before we'll plug it in. And so you can write it down, and then we're going to check and say, does this value make sense? So we get a value of 93.6. We'll put a couple extra digits, 68 grams. Okay, so we're going to do 2 things. We're going to figure out how many significant figures to put. Now, the only number that was unique and was a measured value was 10.5. 2.02 and 18.02 are assumed to be exact numbers because they came from the periodic table. Now we only wrote in 3 or 4, but that's okay. The other thing we're going to do is we're going to estimate how much if 93 makes sense. Now we started off with 5 moles of H2 because every mole of H2 weighs 2 grams and we have 10 grams of H2. So there's a 1-to-1 relationship or a 2-to-2 relationship between H2 and H2O. So I should expect to have created 5 moles of H2O. Now every mole of H2O weighs approximately 20 grams. And if I have 5 times 20, that's 100. Now it's a little less than that, so we should assume that the value created is actually a little less than 100. 93 seems approximately right. So I feel good with that. And then we're going to account for sig figs. We have the 3 sig figs from the 10.5. So we're going to round at the in between the 2 6s for 3 significant figures, shown in green. Showing again, those don't count. And we should have the 6 will round up the 6, so we get 93.7. And grams is the unit, but not just grams, but grams of what we have. Yeah, whenever you have grams or moles, you got to put grams of what? Okay, that's part of the unit. Just having grams is not enough. So sig figs, making sure we have the full units there and that the magnitude makes sense. All those things check out. So I'm going to box my answer. Boxing your answer tells me that this number makes sense and that it's reasonable.